So the analytic procedures for discriminant function analysis is very similar to MANOVA in that it examines a combination of continuous variables. In fact, one of the ways to maybe think about this is it's honestly somewhat like a backwards MANOVA, where we have a categorical DV, the categorical variable is on the DV side, and we can have multiple continuous variables predicting that. So in this case, it combines continuous IVs instead of continuous DVs. DFA creates a discriminant function that are combinations of these IVs, but not necessarily the IVs themselves. And that's important to recognize also that it is looking at the interactions as well. So what's happening behind the scenes, if you will, is that when a function is created, that function is not necessarily just the individual predictive power of the IVs. It can also include multiple interactions between those IVs or portions of those IVs as well. So for instance, if a DFA finds that a particular IV is very predictive but only at low levels, so low levels of that IV on a particular outcome, it might partial that variance into a particular function. So function 1 can be a weighted combination of enjoyment in reading and watching TV. So again, taking a look at the variables and not necessarily looking at them as unique variables, but it may actually increase the strength of prediction of one and decrease the strength of prediction of the other. Function 2 might be a combination, but is uncorrelated with and then unique to function 1. So the other thing is that this is an iterative process. When a discriminant function analysis is conducted, the first question we have is the overall model significant, just like any advanced analysis? And if it's not, we're not going to continue. Once we have a significant DFA, the next question is, what is the strongest function or factor that predicts a particular combination of the categorical outcome? We create that and we partial variance to it. As we create additional functions, we're creating them out of the remaining variance. So generally speaking, your first function is usually going to be your strongest and your most predictive. But remember, it may not capture all categorical differences. Another way to possibly think about this is that it's a series of post hoc tests looking to see where is not the differences between the categories, but where is the variance that predicts those categories, and what are those combinations and how strong is each one. So discriminant functions themselves are extracted based on their ability to discriminate between the groups on that categorical DV. The first function is always the best discriminator, the second is the second best, etc. And by best, we mean how much variance it's explaining and how good it is at predicting. The strength of these discriminators are based on eigenvalues. So an eigenvalue is basically a metric that looks at the total variance within a set of predictors and then partials that variance as we create functions. So one way to think about it is that the number of predictors provides an absolute value of how much variance is in the prediction itself. As we create functions, as we create these factors or functions, each one of them is going to be explaining variance. Now, ideally, we want them to be explaining more variance than any one single predictor. In other words, we're wanting to get above a single predictor. If a single predictor without any weighting or interaction and without any other predictors involved is your better predictor, there's no reason to create a factor or function at that point, because that single predictor is just a good predictor. What we're looking for is functions, groupings of multiple predictors or portions of those predictors, in other words, multiple variants, that actually predicts above and beyond any one predictor. And that's what we use eigenvalues for. We generally want to see any function have an eigenvalue of above 1. If it's below 1, that means that that function or that factor is actually explaining less variance than any one predictor by itself. In other words, a unique predictor without putting it into a weighted variance model. So an eigenvalue is the weight or strength of the function in relation to the set of predictors. It kind of functions like R-square in a regression because it is giving us information of how much variance that function is explaining. Can also look at percent of variance each function explains, and a lot of times SPSS and other statistical packages will give you not only the eigenvalue in its raw form, but also the percentage of total variance being explained by that function. At the end of the day, again, much like MANOVA, what we're doing is we're looking at kind of multi-dimensional space. And the more predictors we have, the harder it is to visualize. But a good discriminant function will have centroids. In other words, we'll have clusters of predictions based on 3 predictors. So for instance, we might find, for example, that mid-range scores on Z, mid-range scores on X, and low scores on Y predict a particular category. We'll call it level A. And level B is predicted by mid-level scores on Y, again mid-level scores on X, but actually slightly higher scores on Z. And finally, the last category is best predicted by high scores on Y, still medium scores on X, and higher scores on Z. Now, at this point, probably X is our weakest predictor, just looking at this particular model of the centroids. But again, it may have a little bit of effect at each level. It may be explaining some variance. And in fact, it may be adding to each function to help that eigenvalue get above 1. So again, as we actually go through with the centroids, we are looking for the center of each prediction. And when we're looking at whether the discriminant function analysis itself is significant, this is what's actually being examined. How well is this total group of predictors at clustering into groups that predict those 3 or more categories? In this case, 3 categories with 3 predictors. The more that the centroids actually clump, the bigger the distance between them, the more likely the DFA is going to be found as a significant total model. And that's the first thing we want to look at. Once we know it's a significant model, then we want to look at how do each of those clusters help us predict those categorical outcomes. So in this case, this is an example visually of a very probably strong DFA, probably very significant, and clearly a pretty good predictor of group membership. So, peeling away the layers of the onion. The first level of the onion is, again, a significance test of the overall model. And again, we're going to use, much like MANOVA, a Wilks lambda, because remember, this is basically just a backwards MANOVA. The Wilks lambda is going to provide a series of omnibus tests that assesses whether the set of functions discriminate between the groups. So how well does this model actually work? It works kind of like a backwards regression. In the first analysis, all functions are included. In the second function, function 1 is removed, and the remaining functions are tested together. Each subsequent analysis removes the strongest function until none remain, keeping the significant functions. So 2 things are happening when we're conducting the analytic procedures in SPSS for discriminant function analysis. Not only are we testing the model that we're going to get, if it's significant, is also going to include the significant functions. So it's going to test all possible functions, but it's going to come back, yes, this is a significant omnibus test, Wilks lambda, and here are the significant functions that you should use for this test. In other words, it's telling us this is the significant model, and here's the functions in that model that this significance represents. So once we have that overall model, we now have to move forward to prediction, determining the specific relationship between the discriminant functions and the IVs. And what we're going to be looking at is the standardized coefficients. They're like betas. And we're looking at where D is the function score, W is the coefficient, and Z is the standardized score for the IV, and K is the number of IVs. So for each discriminant score, we're going to be having basically the constant of that predictor by that predictor. That's our equation. We also will get unstandardized coefficients. They're like B weights, uses the raw IV score instead of a constant. And again, we're going to get correlations like partial or semi-partial correlations that discriminant function analysis are not correlated with each other. So generally, again, we're looking at the correlations between the groups, but we're not that interested in the correlations if we have a significant model. A lot of times we're just making sure they're not highly correlated. If they are, that might, much like any other test, indicate a possibility of a violation of assumption, though for the most part, discriminant function analysis is a fairly robust test. There's only a few violations that we really have to worry about. So generally speaking, this is more of just kind of some it's descriptive information of how the various predictors are associated with each other. Now, to predict group membership, we need to create a classification equation for every group, or in other words, every outcome, where G is the classification score for the group, C is the constant of the equation, W is the coefficient for each predictor, J is the specific group, and K is the number of predictors. So basically, if we have 3 predictors, our equation for predicting categorization in group 1 would be the constant for group 1, in other words, the factor that does the best at predicting group 1, plus the actual coefficient times the value of that participant, and we do that for each predictor and each participant's score. All equations are completed for each unknown case to obtain a classification score for each group. The unknown cases is assigned to the group for which it has the highest classification score. So for instance, if I was wanting to predict Jan's membership on the Underwood, Elvis, Manson question with 3 predictors, I would actually put her equation, her values, into the equation for each group. So the group for predicting Underwood, the group for predicting Elvis, and the group for predicting Manson. And I would calculate her predicted score. The highest score is the prediction. So in this case, we calculate for Underwood 4.2, for Elvis 7.1, and Manson 2.3. So this particular analytic procedure would predict that this person is most likely an Elvis fan. And again, where these numbers come from, and we're going to be running this straight from SPSS, is mainly going to be through practice and going through the lab exercises later in this week. But I really want to get across the point that we're not doing anything new, really. This is basically just a regression equation. But instead of running a single regression equation, we're running it for as many categories as there are by our predictors. So if we had 5 categories, we'd run it 5 times to predict where someone's membership would actually be. Now, effect size. SPSS does not give us an R-squared for each discriminant function, but it can be computed. So again, we want to know how much variance is each predictor explaining. And the way we calculate the R-square for each particular function or factor is we simply would take the eigenvalue for the discriminant function divided by all of the other eigenvalues of the other functions that are significant in the model. So if we had 3 significant functions, one with an eigenvalue of 0.1097, another 0.0287, and one 0.01006, we would add those together. That would be the bottom of the equation. Total variance by eigenvalue is explained by these particular functions. And then we would divide that by the top, the actual value of the function that we want to know. So in this case, we'd find that function 1 is explaining 72% of the variance in this case. So assumptions. Like I said, the DFA is robust in the face of violations of assumptions. We can look at the box M test, but it's fairly sensitive to violations. So generally speaking, the only thing we're really going to check with discriminant function analysis to make sure we've met the assumptions of the test is the box M test. And we're only going to have an issue with it if that is significant at a p-value of 0.001. So we're setting it at basically the box M test really has to indicate that there's a problem with the normality of our data across our actual predictions. And one of the reasons the DFA is so resistant is that it is actually creating possibly weighted factors that are not treating the variables in their original form. So we're already kind of built into this system is a system where it's looking for, shall we say, non-normally distributed variables, and can I take a portion of that variable, like only low-end scores, and use it to do predictions? So in a weird way, it's almost looking for non-normal distributions, and if it finds one, it just grabs the part that's useful to it. So again, the only thing we really are testing for is box M, and once again, that p-value needs to be below 0.001 before we have a problem. Now, what if the box M test is below 0.001? Well, solutions are pretty standard. We go through the process of we can try to figure out which variable may be causing the problems, and that might be where we go back to those correlation matrices, looking for highly correlated variables or variables that we'd expect to be predicted or correlated with another variable that aren't. And we may, once identifying those variables, we might also just look at each variable and find out, do we have non-normally distributed variables? Do we have skewed variables, kurtotic variables, variables with a lot of outliers? And we could remove those outliers. We could also do transformations. We could also interpret the DFA, rerun using the same variables in a MANOVA, and report the Philly trace as an overall multivariate test statistic. So we could also try to flip it back around and basically have a predictor, single IV that is continuous, predicting all the outcomes, and see if that actually provides a multivariate test statistic that is not violating assumptions. The problem with this technique, though, is that we now are having to look at all of the assumptions of a MANOVA because the MANOVA is a little bit more less robust to violations. So this occasionally will work, but it usually doesn't. So again, if that box M test is significant at below 0.001, probably we've got a little bit of work to do, and probably most of that work is going to be looking at the variables themselves and seeing if we need to transform them or remove some outliers. Supposedly, SPSS has been working on creating a solution to this problem. But they've been saying that since version 20, and we're on version 25, and it's still not there. So maybe version 26 will finally give us this solution.